Hello there, Mr. Sorrentino here again, and I'm presenting this video for Math 31 on Section 4.4, Theorems about zeros of polynomial functions. Now, we've already had some of these, some theories about the zeros of polynomial functions, as well as other theorems and rules and such for polynomial functions. But here is where we're kind of putting every little piece together about polynomial functions in order to find any and all zeros of the polynomial function. So we're going to present a few more rules that we're going to use in conjunction with the other rules that we looked at so that we can accurately and completely find exact values of every single zero of a polynomial function. And it also would go hand in hand with you being able to find any and all exact solutions to any polynomial equation as well. So some rules that we're going to be talking about here is that the fundamental theorem of algebra basically says that every polynomial of degree n, with n being greater than or equal to 1, has at least one zero in the set of complex numbers. Basically what that is saying, again, is that the degree of the polynomial is going to have that many zeros, essentially. Now, some of those zeros may count more than once due to multiplicity, which we're going to talk about again with this. So it could be quite easily determined that I have a polynomial expression. Maybe it's a degree 4, but all of the factors are two, or all of the zeros are 2. It can happen. That means it would have a multiplicity of 4. Although we're not going to really get into functions that do that, it is a possibility out there as far as having functions go. So basically, the fundamental theorem of algebra kind of boils down again that the degree of the polynomial should dictate how many zeros that polynomial has, and that you need to account for that many. So if I know if it's a fifth degree polynomial, I need to account for 5 zeros. If it's a seventh degree polynomial, I need to account for 7 zeros, so forth and so on. Non-real zeros. If a complex number a plus bi is a zero of a polynomial f of x with real coefficients, then its conjugate is also a zero of f of x. Basically what that's telling you is that non-real zeros come in pairs. And that's basically as a result of the quadratic formula again. Because remember, the quadratic formula, if I had a quadratic in front of me and I wanted to find its zeros, I would have a discriminant that's negative, but I would usually have, the opposite of b plus or minus the square root of, say, some negative quantity once I did my b squared minus 4ac all over whatever number is down here. Well, that plus or minus symbol is what causes the conjugate to happen. Because if I have, some number plus the square root that becomes an I term over 2, I'm going to have the minus 1 as well. This also works when I'm talking about rational roots or zeros. A polynomial with rational coefficients. If I have a polynomial with rational coefficients, so they have to be not just real, they have to be rational. If a plus c square root b is an irrational zero of the polynomial, then so is a minus c square root b. And I also have the restatement of the non-real zero. So basically, the same thing. So the examples you're going to primarily be given and expected to do on the test are all going to have rational coefficients. As a matter of fact, more times than not, they're probably going to be integer coefficients, which makes them rational, which makes them real, and therefore it's going to obey these rules. So some things to be on the lookout for is that if I have an irrational zero, then its conjugate should also be a part of that. If I have a non-real zero, then I know that its conjugate should also be a zero. And so this helps me to establish additional information along the way. So let's have a look at how we can make use of these things. And also along with this, because irrational zeros have to come in pairs, and because non-real zeros have to come in pairs in the circumstances that you're going to be given. Because again, you're going to tend to be given in most cases polynomial expressions where you have integer coefficients. If it's an odd degree polynomial, because the rationals and non-reals have to come in pairs, then if it's an odd degree polynomial, you should definitely have one rational zero. So this is very important for the circumstance. Now again, this has to deal with a situation where I have rational coefficients. If I have irrational coefficients or even non-real coefficients, all bets are off on these rules here. So, but you're not going to be presented with those in this, at least not in this course. If you want to take some advanced mathematics courses, maybe you'll have that happen to you, but not this one. So, how do we make use of these rules we just talked about? We want to find a polynomial function with rational coefficients of the lowest possible degree with the following zeros. Okay. So we know that we have 2 as a 0, -3 as a 0, 5i as a 0, and square root 11 as a 0. Based on the rules, and this says it has to be one that has rational coefficients, I know that I have two other zeros here. -5i is going to be a 0 because that's the conjugate of this one. And negative square root 11 is going to be a 0 because it's the conjugate of this. So there's two more zeros that I automatically have to have because I know it's a polynomial function with rational coefficients. Now I have to try to figure out what this polynomial is going to be. And I'm going to be doing a lot of foiling and multiplying and so forth. So for it to be having the lowest possible degree, these would be the only zeros I'd expect. I mean, I could come up with other zeros to just make up a zero. It also has a 0 at 7. But I'd be adding extra zeros and therefore adding more factors, which means I'm raising the degree of the polynomial. So for it to be the lowest possible degree, I'm going to just assume that these are the only zeros, which means that this polynomial function, which I'm just going to call f of x, is going to have, well, since 2 is a 0, x minus 2 is a 0, is a factor. Since -3 is a 0, x minus -3 would be a factor, which means x minus -3 becomes x plus 3. Since 5i is a 0, that means x minus 5i would be a factor. And we already established that -5i had to be it as well, so x minus a -5i, which become x plus 5i, is also a factor. Square root 11 is a 0, so x minus square root 11 would be a factor. And since negative square root 11 was also a 0 because it's a conjugate, x minus square root 11, which would become x plus square root 11, is also a factor. So now what I'm going to do is get some foiling going on, some multiplication and distribution going on here. So I'm going to do these two together because they're conjugates. The same thing with these. The fact that they're conjugates makes it a little nicer multiplication, because if they're conjugates, going back to what we talked about with conjugates before, in conjugates, when I have the same two terms just separated by a different sign, when I do the foiling process, the O and I part, the outside and inside portions, cancel. So I can actually take a shortcut and say, well, these is going to be x times x, which is x squared, negative 5i times positive 5i is a minus 25i squared, which is not something we would tend to write it in that format. So I could say that that's going to be x squared plus 25 because I squared is -1. And likewise with this, I can skip I can skip this multiplication and this multiplication because again in that process, since they're conjugates, the O and the I part of the foiling process will cancel out. Same thing with this. X times x is x squared. Negative square root 11 times positive square root 11 is going to give me a minus 11. If I multiply x minus 2 times x plus 3 through, I'm going to have x squared plus 3x minus 2x minus 6, which becomes x squared plus x minus 6. This one has 3 terms in it. The other ones have 2 terms. So I'm going to multiply these two together next because it's a little bit easier at that point. So I can rewrite f of x as x squared plus x minus 6. X squared times x squared is x to the 4th. X squared times a negative 11 is a minus 11x squared. 25 times x squared is a plus 25x squared. And 25 times a negative 11 is going to give me a minus, whatever 25 times 11 is, 275. And so if I can combine some like terms on that one, I'm going to have x to the 4th plus 14x squared minus 275. And then lastly, I'm going to have to distribute one last time to get this final expression, which means I'm going to do x squared times x to the 4th, which is x to the 6th, x squared times 14x squared, which will give me a 14x to the 4th. X squared times a negative 275 is a minus 275 x squared. No, that takes care of this one. The x's, I'm going to say x times x to the 4th is going to give me an x to the 5th. X times 14x squared is going to give me a 14x cubed. The x times a negative 275 is going to give me a minus 275x. And then lastly, I'm going to even do a slightly different color. Do any lighter greens are available on this. Go to that lighter blue. Negative 6 times x to the 4th gives me a minus 6x to the 4th. It's the same procedure we often use for foiling. Negative 6 times 14x squared. It's going to give me a minus 84x squared. It's just that you have to just make sure you're keeping track of, which quantity in the first one are you multiplying to the quantity in the second one. And negative 6 times a negative 275 is going to be a plus 1650. And then I look to combine some like terms. And I want to write this in standard form. So as I combine these like terms, I'm going to want to make sure that, I start with the highest power and work my way down. So x to the 6 was like it's the highest power up here. X to the 6 is the only term that has it. So I'm going to write x to the 6, which means I kind of took care of this one. The next one I have is x to the 5th. I only have one term with x to the 5th in it. That's this one. So plus x to the 5th. X to the 4th will come next. I have 14x to the 4th minus 6x to the 4th. So I'm going to have plus 8x to the 4th. Takes care of these two. The x cubed would come next. I do have a 14x cubed and only one x cubed term. Takes care of this one. X squareds would come next. I have a negative 275 x squared minus an 84 x squared, which means that I would have a negative 359 x squared. X terms are next. I only have a minus 275x. And then constant term plus 1650. So this would be one possibility. The other possibilities would just be multiples of this. I should expect to have a 6-degree polynomial because I've been able to define having 6 zeros. Could it have more? Yes, but we were working under the assumption we wanted this to be the lowest degree possible, and if I made it any higher degree, it's going to have more zeros. Or I had to put multiplicity on some of these, but that's also going to make the degrees higher. Anything beyond this, I'd be me multiplying this, I saw that the same factor, so I'd just be multiplying this whole thing by a single constant, and therefore I could have variations on that and have different maximums and minimums as a result of that, but ultimately this, would be the main function, and the other ones would be multiples of this function. So that's kind of lengthy, and there's a lot of multiplication going on, but they do ask questions like this, maybe not as severe. I'm trying to give examples that have the non-real and irrationals in them, whereas they may give you a lot of ones that have one or the other, just not both. Now, so, this helps, so working this in reverse also helps you keep track of what zeros you should expect to have along the way. And if you're able to say, well, I figured out the square root of 2 is a 0, well, then you should expect the negative square root of 2 to be a 0 too. So now another thing that we can use to help us identify rational zeros is called the rational zero or rational root theorem. So let's have a look at that rule. The rational zeros theorem, which is also known as the rational root theorem, sometimes it's known as the rational root test. If you're given a polynomial where all the coefficients are integers, so which is generally what we're going to be facing in most of the examples you're going to be given, so they're all integers. If p is a prime factor of a sub 0, and q, now again, they're not assuming this p out here, they're assuming this is a different constant. They probably should have put this in terms of f to make it more clear. I don't want you getting confused that this p and this p represent the same thing. They don't. Okay. We let p be a prime factor of a sub 0, which means a sub 0 is the constant term. And q is a factor of a sub n. A sub n is the leading coefficient. Then any rational zero of f of x would be of the form p divided by q. This used to be a big deal before the dawning of calculators and other things that, are used typically today. The reason being is typically if, a mathematician was looking to find the zeros of a polynomial, and looking at the one we have in example 2, we could say, okay, I expect up to 4 zeros here. So let's just try to plug some numbers in and find them. Now, first of all, I don't even know if it has any rational zeros. This thing has an odd number of terms, so I'm not going to be able to group and factor or use any other techniques that we're familiar with as far as factoring goes. There are methods taught in some older textbooks which teach you how to split middle terms, but that's a lot of trial and error. And even with that, those factoring methods don't necessarily work nicely if you have irrational numbers as solutions. So they would basically be left with no choice than to go through and just kind of list numbers, try them out until they are able to find some. Now, if you follow that, you can say, okay, well, this one's getting closer to 0. I'm on the right track. If I say I gotta go from 2 to 3 and it's getting further away from 0, then I'm saying, okay, well, maybe I'll go in the other direction and maybe try out 1, -1, zeros, any of that stuff to see if those work, and then maybe try some fractions. But the fact of the matter that you have so many different fractions involved, if I find out like by the intermediate value theorem, hey, this one has an answer between 1 and 2. There's a lot of fractions between 1 and 2, like 1.1, 1.5, 1.05. There's a whole bunch of different things that, are rational that could possibly have zeros. So, you know, basically they were stuck with having to go through quite a large number, basically an infinite number of possibilities. This at least broke it down into a tangible, finite list of numbers to try out. Here's how it works. So I'm looking at the leading coefficient and I'm looking at the constant term. So one thing I definitely want to do if I'm going to be using the rational zero theorem in any shape, form, or manner, and usually if I'm looking to find zeros or I'm looking to graph the function, I should probably have it in standard form anyway. Q are the prime factors of the leading coefficient. So I got to think, well, what integers go into 2? Well, it's not a whole extensive list. I have plus or minus 1 or plus or minus 2. Those are the factors. The factors known as P, well, what numbers multiply to give me a -15? Or what numbers can I divide into and get no remainder? Well, plus or minus 1, plus or minus 2, no, plus or minus 3 would, plus or minus 5, or plus or minus 15. That's my list. Now, the possible rational roots, or zeros. I just take every possibility of P divided by Q. So 1 divided by 1 would be plus or minus 1. 3 divided by 1 would be plus or minus 3. 5 divided by 1 would be plus or minus 5. 15 divided by 1 would be plus or minus 15. Plus or minus 1 divided by plus or minus 2 would give me plus or minus 1/2. Plus or minus 3 divided by plus or minus 2 would give me plus or minus 3/2. 3/2. Now, if you wanted to write these as decimals and say that was 1.5, that's also acceptable. Plus or minus 5 divided by plus or minus 2 is plus or minus 5/2, also known as 2.5. And plus or minus 15 divided by plus or minus 2 is plus or minus 15/2, which would be plus or minus 7.5. So even though I have an infinite number of possibilities, before this, I applied this theorem, now I have this whittled down into 2, 4, 6, 8, 10, 12, 14, 16 possibilities. So if you're going from an infinite number of possibilities down to 16, that's a big deal. Now, with the dawning of calculators and things like that, and using graphing techniques more often, it's a little easier nowadays. I could certainly use other things to much more quickly identify what the rational zeros are. Now, this list of possible rational zeros are only possibilities. Remember, this thing only has 4 zeros. I'm listing 16 numbers as potential zeros. Obviously, all of them are not going to be zeros. Some of them are expected to be zeros, and that's only if I do have rational zeros. I may not. So, this would be the list I could choose from to go through, plug this into the polynomial, and see if I do in fact get 0. And that's something that you could use to benefit you. Again, with the calculator, how do we use this nowadays? Because ultimately the calculator, I can identify what the zeros are. Okay? I could graph it on my calculator, use the calc feature, have it find zeros for me, and then find that. But sometimes the decimals I get as reports are a little bit off because it uses a version of the intermediate value theorem to kind of zoom in and hone in on a number. And once it gets close enough, it says, okay, that's the 0. So if I'm looking at a number And say I graph this, and I saw like, something along the lines of 2.49998876 as an answer. Well, I'm thinking, well, that looks like it's about 2.5. Is 2.5 a possibility here? Well, from my list of rational roots, yeah, it is. It's worth something to try out. It looks like it might be irrational because I don't see any kind of set repeating pattern, but it could be just be reporting that way on my calculator because of the way it comes up with the answer. Um, so what we could use it nowadays for is I can look at this and I can focus just my attention on that leading coefficient and say, well, since the only numbers that go into that leading number are 2 and 1, any answers I would get that are rational should be integers, or they should be halves, which means I should see 0.5s. And I also could reduce it and say, okay, well, the integers should be multiples of 15. And so if I say, like, well, is 12 going to be a possible answer? Well, no. If it looks like the graph is passing through at 12, no, I don't expect that to be an answer. So it's probably not going to be 12 exactly. It's going to be 12 point something or other, and it's probably going to be irrational. Or it means I didn't graph it right to begin with. So the rational zero theorem is used a little differently nowadays since the calculators can aid us. Now, again, as we move into and go further into this year, this semester, you're going to be doing less and less with the calculator. When the final comes along, you're not going to have the calculator to aid you necessarily. On the initial test, you will. So you can use the calculator to identify what the zeros are, the rational ones, but since you're going to be asked to find the exact values of all of them, then you're going to need to, get those factored out and deal with that. When you get to doing the final, obviously, in some cases, you might have to be given a zero in order to find the rest of it. Or you'd be given something that maybe has a small list of these possible rational roots to do it. And then, you could look out for your zeros that way. As I mentioned here, this is a tedious process, but you can then figure out that f of 1 is 0 and f of negative 3 halves is 0. So on my list, I end up finding out that the only rational ones that actually are zeros are negative 1. Was it negative 1? Yeah. No, 1. Positive 1. It was negative 3 halves. And negative 3 halves, which were the actual zeros. 3 halves. The rest of the possibilities weren't zeros. So, once you establish those, well, I want to find the rest of the zeros. You notice when I look at the graph of the function, pull it back over here a little bit. But look at the graph of the function, it looks like just a parabola. And no matter how far out I go, I don't see any more turning around. And it doesn't take me long to come to that conclusion because it is a degree 4. I do expect the two ends to be pointed in the same direction, ultimately, so they are. I don't expect any more turning around at any other point. I do expect to see 4 zeros. I've established 2 of them which are rational, but chances are the other 2 are going to probably be non-real, and they're not going to show up on the graph ever. How do I find out what those are? Well, that goes back to the techniques we were talking about beforehand. I've established the rational zeros. Let's find the rest of them. So I'm going to go back and rewrite my function, f of x equals 2x to the 4th plus x cubed plus 7x squared plus 5x minus 15. And by using the rational zero theorem, it will help the calculator as well, I've established that x equals 1 and x equals negative 3 halves are zeros. I want to find the rest. So I want to find ones that are rational. Either they're irrational, which unlikely, I'm not seeing them show up on the graph, or they're going to be non-real. So, and chances are I'm expecting them to be non-real because I'm not seeing any other ones show up on the graph. But I do know at least with if I factor out the factors that go along with these two zeros, I'm going to be going from a degree 4 down to a degree 2, which is quadratic, and I can handle that using other methods. So let's deal with that. So let's give myself a little bit more room, maybe zoom in a little bit. So I want to break down that f of x further. So I'm going to use synthetic division to break it down because I now know that x minus 1 and x plus 3 halves are factors. And again, that comes from the factor theorem and just putting an x minus in front of these two zeros. I use the zeros though for my division because I'm going to use synthetic division. So I'm going to rewrite the coefficients. I have a 2x to the fourth, a 1x cubed, a 7x squared, a 5x, and a minus 15. So no missing x terms. And I'm going to do the 1 first. Doesn't matter which one I do first. So basically this division is going to factor out the x minus 1. So I'm going to bring down the 2, multiply by the 1, I get a 2 here, add, I get 3, multiply by 1, I get 3, add, I get 10, 1 times 10 is 10, add those, I get 15, 1 times 15 is 15, negative 15 plus 15 is 0. Which, that's what I expect it to be. Now, I'm not going to stop my division here, because if I stop my division here, this basically would let me say at this point that f of x equals x minus 1 times 2x cubed plus 3x squared plus 10x plus 15. I want to break that down further because I know there's another factor. That one. And it doesn't look like there was any multiplicities when I was doing that either, so I don't have to, if I saw a multiplicity on 1, I would probably try to factor it again and see if it indeed was. But, I didn't see any evidence of that. I didn't see any flattening. I didn't see it just touching at 1 and moving on. So we're good. All I'm going to do now is, I've taken care of this one. I want to now take care of this one. So I'm just going to start with this list of coefficients again and divide by the negative 3 halves. Bring down to 2. Negative 3 halves times 2 is a negative 3. Add those, I get nothing. Negative 3 halves times 0 is 0. Plus 10 is 10. Negative 3 halves times 10 is a negative 15, which gives me a 0. So now what this means is that I've broken this down even further now. The x minus 1 is gone, because I did that in the previous step. The x minus negative 3 halves, which is x plus 3 halves, is now factored out. And what I'm left with is, well, this is my remainder, this is my constant term, this is my x term, this is my x squared term. So I have 2x squared plus 10. So I have this factored, and remember, I'm still looking for the zeros. Well, obviously, by the zero product rule, either x minus 1 equals 0, which of course gives us the x equaling 1 again. That part's repetitive. I already knew that was a 0. I didn't really need to reestablish that. Same thing with this. X plus 3 halves is a 0. Again, that gives me the x equals -3/2, which I already established was a 0 from use of the rational zero theorem and also making use of the calculator to a certain extent. It's this one I was mainly focusing my attention on, the 2x squared plus 10 equaling 0. If that equals 0, that would also produce a 0 of the polynomial. So I'm going to subtract 10 from both sides. I'm going to divide both sides by 2. And then I'm going to square root both sides. And I'm going to put the plus or minus symbol over here. But when I square root a negative, that goes along with saying that I'm going to put that I on the outside. And that represents my two non-real zeros. So if I wanted to state at the end here, my zeros are x, and I'm just going to write it as a list. I have -3/2. I have 1. I have I square root 5. And I have -I square root 5. That's a list of 4 zeros, which is how many I expect. That's my solution set. There's one other rule that we're going to look at to aid us a little bit, although again, it's a rule that has a little bit of use, but it's not necessarily a huge use. I mean, it does help us establish some things along the way, and that's called Descartes' rules of signs. So let's have a look at that. So for Descartes' rules of signs, this is another thing to help me determine how many zeros I could expect. I mean, we had the rational zero theorem which said, okay, we can expect this many rational zeros. These are possible rational zeros. And we had a list that we could try and see if there are them. Descartes' rules of signs deals with helping us determine how many positive real zeros and negative real zeros that we could come up with. This helps us establish the real zeros so that we can say, okay, well, if we're getting this, then we can expect maybe some non-real zeros along the way. It's saying that let P of x be a polynomial with real coefficients written with the powers of the roots in descending order or ascending order. So basically, I mean, if we write this in standard form, we're good. The number of positive real zeros of P of x is either equal to the number of variations in signs in P of x, or equal to the number of variations in signs in P of x minus an even integer. Now, what that means is if I have all of the x's, the powers of x is represented, again, I don't have to worry about any zeros because those don't consider changes in sign. All I'm looking is at the signs to see if they change or anything in between them. That's going to help me figure out how many the possible number of positive real zeros I could get, and negative real zeros. I'm just going to take the polynomial function, replace it with -x, simplify that, and then compare the sign changes and make a very similar determination. So let me demonstrate that on A, and let me have you give it a try on B. So with A, when I look at f of x, now I have a 4 that's positive, so it goes from a positive term to a negative. That's one sign change. Then it goes from a negative to a positive. That's another sign change. So I'm up to 2 sign changes. When I go from the 7x cubed to the 2x squared, there's no sign change. So right now I have 2 sign changes. I then go to a -8x. That's a third sign change. And then I go to the +1, which is a fourth sign change. So f of x had 4 changes in sign. That means the number of positive real zeros is going to be either 4 or that number minus an even integer. So if I subtract 2, I could have 2. If I subtract another 2, or none. So I could either have 4 positive real zeros, 2 positive real zeros, or none. One of these has to be true. I then look at f of negative x. Which would be 4 negative x to the 5th minus 6 negative x to the 4th plus 7 negative x cubed plus 2 negative x squared minus 8 times negative x plus 1. Negative x times negative x raised to the 5th power is a negative x to the 5th, and times 4 is going to be a negative 4x to the 5th power. Negative x to the 4th is a positive x to the 4th, times a negative 6 is going to be a minus 6x to the 4th. And I keep doing the simplification, making sure I'm accounting for the powers. Negative x squared is positive, so this is going to be a plus 2x squared, a plus 8x, a plus 1. So f of negative x has now been established and simplified. And now I look at the variation, the sign changes in this. I go from a negative 4x to the 5th to a negative 6x to the 4th, no sign change. Going from the next term, no sign change. Going from the negative 7x to the 3rd to the 2x to the squared, there's a sign change. So I have one sign change. And then the rest of them are positive. So here I have one sign change. So the number of negative real zeros is 1, and that's it. Because if I try to subtract an even integer from that, I'm going to get negative. I can't have negative. I can't say, well, I have negative 3 negative zeros. That doesn't make sense. So this pretty much tells me that this function here is going to have one negative real zero. So I know it's guaranteed to have one real zero. Okay, it's a 5th degree polynomial, so it could possibly have 4 others that are positive. It could have 2 others that are positive, which means I would probably have another 2 that are non-real. Or I can have none that are real, or positive and real. That means that the rest would have to be non-real. So again, this kind of thing can help me figure out what kind of answers to expect. Because if I come up with an answer and I come up and say, oh, 2 of the zeros for this, are negative 3 and negative 6. Well, that's impossible, because this should only have one negative real zero. So, or if I state an odd number of positive real zeros, well, that's impossible as well. So, this is helpful to a certain extent to kind of eliminate possibilities and kind of knowing what you're expecting to see. Let's go to B. Then let you try it. I want you to tell me how many possible numbers of positive real zeros there are, and I want you to tell me how many possible numbers of negative real zeros there are in B, and then we're going to go over it. For B, let's start with f of x. For f of x, I start with, now these are written in order. I don't have to have zeros between them. I'm good. So I have a negative 9x to the 7th to a 4x to the 5th. That's one change in sign, to a positive, to a positive, to a negative. So I have 2 sign changes. That means that I have, as far as a possible number, of positive reals, I have 2, or I have none. So I'm not going to have an odd number of positive real zeros here. So if I say, hey, the solutions to this are 7, 3, and 5, that's three of them. It isn't, because I can only have two, only maybe two of them will work, maybe none of them will work. I can't have an odd number. I can't have anything over 2 being a possibility. I certainly can't just have one of them. So now I'm going to do f of negative x. And as a shortcut, anything that has an odd degree is going to have a sign change when I do f of negative x. Hopefully you've noticed that now. So anything that has a odd exponent on the x is going to have a sign change. So this is going to become a positive 9x to the 7th. This is going to become a minus 4x to the 5th. The x squared is going to stay the same. The 9x is going to have a sign change because that's an odd power. And of course, the minus 2 has no x on it, so changing it to a negative x won't do anything. And now I see that I have 1, 2, 3 sign changes. And therefore, when I look at the possible number, should actually have that up here too. Of negative real zeros, I could have 3 of them. I can subtract an even integer of 2, which can be or 1 of them. And if I subtract 2 from that 1, that's going to be negative. So I'm either going to have 3 of them or I'm going to have 1, which means I'm guaranteed to have at least one negative real zero on this. So if I don't come up with a negative real zero on this, I'm doing something wrong. Now again, this particular rule here doesn't really help me establish what they are, but it does let me know what I can expect as possibilities, which in the end can help me zero in on an answer. Now for example 4, this is a lengthy video here, and this last part is going to be quite involved because I'm going to incorporate a little bit of everything we've learned so far in this chapter into this. So let's have a look at example 4 and go from there. So for example 4, you're given this 7th degree polynomial function. Sorry about the big wonky plus sign there, but there was a sign error that I noticed when I made the slide. I fixed in the notes, but didn't fix it here until there. I'm being told that the x equals 2 plus the square root of 3 is a 0 of f of x. I'm asked to find the remaining zeros. So a couple things I know about this function based off of the rules we've established so far, and I'm going to list them right here. First, based on the degree of the polynomial, I expect to see 7 zeros. Now, I don't know if those zeros are going to be all real. They're going to be rational, irrational. I don't know if, anything beyond that at this point. If any of them are going to count more than once and have a multiplicity, I have to wait to see more, do more detailed work into this function to find out more information. But I do know I expect to have 7 zeros, one of which was given to us already. So there's 6 more I have to find. I know at the end behavior, it's going to look like that. Is that important for me, as far as finding the zeros go? I mean, if I'm going to use some graphing techniques, which one this complicated, you definitely should. Um, it's good to know if you have what would be a complete graph in front of you, and if you're not seeing that, and behavior working well or as anticipated, then that's a sign that you may need to see more of the graph to make your conclusions. Um, because it has an odd degree, and I know that any non-real zeros have to come in pairs because all these are integer coefficients, which makes them rational. And since I know that any irrational zeros have to come in pairs, that means I have to have it. I have to have at least one rational zero. Um, some other information I can deduce from this. If I'm going with Descartes' rules of sign here, f of x has 1, 2, 3, 4. Let me take that back. 1, 2, 3, 4, 5, 6 sign changes. Which means I can expect to have either 6 of them, 4 of them, or none of them. F of negative x, which is basically going to be, having this is a negative, this is a positive, that would still be negative. Although all the odd ones are going to change sign. This is going to be negative, that's going to remain negative, that's going to be negative, that's going to be positive, that's going to become positive, that's going to stay positive. So basically I'm going to have one sign change. Now if you want to verify and plug the negative x in and make sure of that, but it has one sign change, which means I'm going to have one possible negative real zero. So that's a sign that I'm going to have at least one real one. Now, is that going to be my one rational zero? I don't know. Um, I actually have no positive real zeros, but I know I have to have one that's negative real zero, and it could be my rational zero too. So there could be some movement between these two. But I just want to make sure that I verify that as I go along. Now, the fact of the matter is, I know that I already have one positive real zero because 2 plus square root 3 is one of them. So I know I'm not. So I know zero's out up down over here. So I'm gonna probably have to have at least two other. I mean, at least three other possible real zeros as well. I mean, so again, this helps me figure out what kind of answers to expect. And the last thing I can look at when I look at my rational zero theorem, um, my rational zeros, because the leading coefficient's a 2, I mean 270 has a lot of factors. So me listing all the possible factors it'd be quite a lengthy list. But because the leading coefficient's 2, I would expect to either have integers or something of the format where I have a number, a decimal point, and a 0.5 because I'm dividing by 2. Those are other things I'm looking at. So that's a lot of information so far. It doesn't actually zero in on what any of the zeros are, at least the other 6 I'm looking for, but at least I know some things about this that will help me stay away from, other, pitfalls. Now, what I also chose to do at this point is I did a quick graph. Now, you're not going to be given many of these that are degree 7. I mean, I wanted to include one that had a little bit of everything in it. A lot of the ones you're going to deal with aren't going to have all the aspects, all the types of zeros, and have multiplicities, and some of them are going to maybe have a multiplicity but have no non-real zeros. Some of them may have, you know, some irrational zeros, but the rest will be rational. And they have no multiplicities. There's going to be different variations of them. They're not going to have all the characteristics in all of them either. So I'm just trying to pick one that kind of talk about all the talking points so you can see that. So don't expect everything to be quite this complicated. I just want to make sure I picked an example that had, a little bit of everything in it so we kind of show how we can incorporate everything we know. When I did a quick graph of this on my calculator, and I'm not going to go into like the minimums, maximums, and the settings I put on it. The graph I got, this is an integer, 3. 3 is a factor of 270. So by, again, going back to the rational zero test, that is definitely a possibility. Negative 1.5, which is 3 halves, is also, if 3 is a factor of 270, so is 270 of the 270 over 2, and so is negative 1.5. So, those are both possibilities by the rational zero test, so those are good contenders. I also see right here that at x equals 3, the graph is touching the x-axis but not passing through, which indicates this has a multiplicity of 2. That means when I count x equals 3 as a 0, I count it twice. So on the right hand side, my positive real zeros, I have 1, 2, 3, 4, which is definitely a possibility here. And as far as possible negative real zeros, well, this one is my negative real zero. I know I had at least one rational zero possible, but I have 2 here, so I did meet that category. I know this is a complete enough graph because it's obeying this. 7 zeros. Right now I'm accounting for 1, 2, 3, 4, 5 of them. I know that chances are I'm not seeing any signs that I'm going to have 6 positive real zeros here. That means there's 2 that are non-accounted for. And because the end behavior is acting the way it should be, I'm going to probably expect that the other 2, I'm going to have 2 of these that are non-real. Along with that, now that's what I'm going to be ultimately looking for on this. I'm going to be trying to locate and find out the value of these 2 non-real ones because I've already established most of the other ones because this my calculator gave me, this my calculator gave me. This one is irrational, but this also happens to be what 2 plus the square root of 3 is. Because that was told me to me that was a 0. But because this is, my original function was f of x had, integer coefficients, which means that they're all real number coefficients, they're also all rational, that if 2 plus square root 3 is a factor, or a 0, 2 minus square root 3 is also a factor, and that's what this one would be. So I know what all of my real zeros are at this point based on the information I was given in the problem and the graphing and the analysis I did. What I have to do now is figure out what those 2 non-real zeros are. And that's where most of the rest of the work's going to be, just to find those 2 other zeros. So right now I've established 4 other zeros. I have 2 minus the square root of 3. I have negative 1.5, or negative 3 halves. And I have 3, which counts twice, because it has a multiplicity of 2. There's 2 other zeros I got to find. So what I'm going to need to do is use what I've found thus far and take that f of x and factor it down so I can find what those 2 non-reals are. And I'm going to do that in using 2 different other facts. So let's give myself a little bit more room. Well, what I need to do is go, now having the zeros, I got to figure out what my factors are. So my factors of f of x, I'm going to have x minus a negative 3 halves, which is x plus 3 halves. That gives me the x equals negative 1.5 as my 0. I'm going to have x minus 3 as a factor. I'm going to put a little square on that to indicate it has a multiplicity of 2. I have an x minus 2 plus the square root of 3 and x minus 2 minus the square root of 3. Those would give me the 2 minus square root 3 and the 2 plus square root 3 as my other zeros respectively. I need to divide these out of f of x, because if I do that, that's going to take my degree 7 polynomial. These will account for 5 of those degrees. What I will be left with once I factor these out is another second degree polynomial, which I can certainly find the zeros for, and those zeros are going to be the ones that are more than likely the non-real ones. So how am I going to do that? Well, these, since they are essentially my situations where I have a linear binomial with a leading coefficient of 1, I could do synthetic division with these. These, on the other hand, they're not synthetic friendly. So chances, and that's because, like, I could try that, but I'm going to have a lot of irrational numbers along the way trying to deal with it. It's not going to work out very nicely. It's going to be really clunky, and you know, I really don't want to have to use synthetic division with those. So, but what I can do with those is multiply them together. So if I take x minus 2 plus the square root of 3 and x minus 2 minus the square root of 3, and I multiply those through, I'm going to have x squared minus 2x minus x square root 3 minus 2x plus 4 plus 2 square root 3 plus x square root 3 minus 2 square root 3 minus 3. So if I take each term of the first quantity and multiply it to each term of the second and multiply it out, I would get these. When I combine some like terms, I have x squared minus 2x minus another 2x is a minus 4x. The negative x square root 3 and the positive 1 cancel. I have a plus 4 and a minus 3, that's a minus 1. The 2 square root 3 and the minus 2 square root 3 cancel. So I have this. So I now can say, well, now this is a factor. And this I will eventually long divide. Because I can only do synthetic division with linear binomials with leading coefficients of 1. This is no longer that, but it would be probably a lot easier to use this than to use the linear binomials that happen to have irrational numbers as part of them. Now, which order do I want to do these? Do I want to do the synthetic divisions first and then the long division, or vice versa? In the end, it really doesn't matter. They should, I mean, each time I factor one of these out and carry through the division, I should get a remainder of 0. I should get a nice polynomial expression that is my quotient. However, I could save myself a little work if I do the synthetic first, because again, with long division, the bigger the difference between the degrees of the two things I'm dividing, the more steps it takes. If I started by doing my original polynomial, which is a 7th degree polynomial, and dividing by this square polynomial factor, it's going to take a number of steps to do it. Whereas if I factor out these three factors, including the 3 twice, with synthetic, I'll be down to a degree 4 polynomial. And when I divide that by a degree 2 polynomial, that's far less steps. So that's the route I'm going to take with this, and that's what I'm going to use. So, so let's go with that. Give myself a little bit more room. So I'm going to go back to my original function. I'm not going to rewrite it here because I have it in front of me. You'll have it on your paper. I'm going to rewrite the coefficients. So I'm going to say, okay, I'm going to have 2, negative 21, positive 92, negative 228, 236, 423, negative 1134, and positive 270. And I'm going to carry through the synthetic division. Now, it doesn't matter which order I do them in. I'm going to take care of the 2 3s first. I'm going to do one synthetic division with 3, and I'm just going to go in fast motion with this and carry it through. So that's the first synthetic division of 3. This would be a 6-degree polynomial if I decided to write it out, but I'm not going to bother with that because I really don't want that 6-degree polynomial is no use to me. Let's break it down further. I'm going to carry through another synthetic division of 3. Had a few things I was putting in the wrong spots there, but that's what you would get when you carry through the synthetic division with the 3. Again, this really is no use of me yet because I still have another linear binomial, so now I'm going to use the negative 3 halves. But right now, taking care of these guys, I can now say with the synthetic division that f of x is now x plus 3 halves x minus 3 squared times, now again, going with it, this is now should be a 5th degree polynomial. So I'm going to have 2x to the 5th. Maybe it's 4th. Let's see, 1x squared. Yeah, it's x to the 4th minus 12x cubed plus 38x squared minus 84x plus 20. Okay, so now I have this. This is now what I'm going to be dividing by this quadratic factor. Now I'm going to do my long division. So now I'm going to set up my long division. So now I have this all broken down. Now I'm ready to actually factor out the and do the long division up here. And before I do that, though, I did notice one error as I was just looking at it. When I combine the 4 and the minus 3, it should be a plus 1, not a minus 1. That would make a big deal. Sometimes a little mistake like that can certainly cause a lot of issues whenever you are doing so much of this work here that a simple plus in the wrong place or a minus in the wrong place can throw everything off. So that's why it can be very important for you to pay attention to what you're doing. Make sure that you're computing things correctly along the way. So I'm going to do that I'm going to set that long division. So I'm going to have my 2x to the 4th minus 12x cubed plus 38x squared minus 84x plus 20. And I want to divide that by x squared minus 4x plus 1. Now again, I'm not going to talk step by step through the long division process. We've already talked about long division. I'm just going to carry it through so you can see what you would get, but certainly you should practice this as well. So I'm just going to do the work and then resume talking. So I got my remainder of 0, and I now have this broken down even further. So now I can rewrite f of x I still have the x plus 3 halves, the x minus 3 squared. Scooch this over a little bit. I now have the factor 2x squared minus 4x plus 20, which is what the quotient was. And that's because I factored out the x squared minus 4x plus 1. So that's the factored form. Now it's all linears and quadratics. The thing is, I don't have to worry about this because this is what gives me the negative 3 halves as a 0. I already know that. I don't have to worry about that. This gives me my x equals 3 as a 0. I already know that. This is what I factored out through the division here. I already knew that was a factor, and the two roots I got from it are the 2 plus square root of 3 and 2 minus square root of 3. With this equal to 0, what I'm really just concerned about is this one. This is the one that's going to give me my non-real zeros. So 2x squared minus 4x plus 20 is set equal to 0. Everything's divisible by 2, so it makes my life a little easier if I just divide everything by 2. I'm not even going to try doing anything but the quadratic formula. I mean, factoring, you know, it's not going to work because I already established that this is going to probably be where my non-real zeros are from. I just did it ahead of time, so I'm not going to use a strategy that doesn't work with it. Completing a square, again, is usually a version that people don't like, so I'm just going to go and use the quadratic formula on this, and that's going to give me, which simplified further becomes, which is finally. So now I've established all of the other zeros. So I'm going to go back up and answer the question now. Find the remaining zeros. I don't want to move that. So the remaining zeros are 2 minus the square root of 3, negative 3 halves, 3. I don't have to list it twice, but I might want to indicate it has a multiplicity of 2. I have 1 plus 3i, and I have 1 minus 3i. So that's a grand total of 1, 2, 3, 4, 5, 6. 6 additional zeros that are given for degree 7, and I was already given 1. So everything's accounted for. That's the solution. So very intense work on this one. You're not going to usually be given something this intense. Again, I just wanted to pull an example out where a little bit of everything had to be used, so you could see it all in action. Because it's possible, but you're not going to probably be presented with many instances where that has to be done. So, but use what you learned here. Practice some other functions from your textbook. Ask any questions you have in class, or come and see me during office hours to get some additional help. Until I see you in class or in office hours, or until the next video, I'm going to bid you good day, and I'll see you around. Bye, everybody.